In addition to our reciprocal and Pythagorean identities, we will now add the even and odd identities. Now, to help you understand where these come from, I want to remind you of the definition of even and odd functions from algebra. A function f is even if f of negative x equals f of x. The graph of an even function is symmetric about the y-axis. So this algebraic test that we have listed here reveals the fact that if I have an x and a negative x, that is a positive argument, we'll call it x, and a negative argument, negative x, where the function values or the y values are the same, then those 2 points are reflections of each other across the y-axis. So even functions, therefore, are symmetric across the y-axis. On the other hand, a function f is odd if f of negative x equals negative f of x. That is, the graph of an odd function is symmetric about the origin. To understand this graphically, notice that the argument is opposite in sign on either side of the equation. So I have a positive x and a negative x. That places me on either side of the y-axis. Also notice that the function value, the sign to the left of f, is opposite. So whereas f of negative x has a positive value, f of x has a negative value. This creates symmetry about the origin. Symmetry about the origin is a type of rotational symmetry. Or another way that you can think about symmetry about the origin is in terms of two reflections. If I take this point and I reflect it across both the x-axis and the y-axis, I land on the other point. So even functions are symmetric about the y-axis and odd functions are symmetric about the origin. With this graphic overview in mind, let's see if we can work example 7. It says, use the graphs below to determine if the sine, cosine, and tangent functions are even, odd, or neither. So looking at the graph of the sine wave, I want to determine if it's symmetric about the y-axis or the origin. Now, for a function to be symmetric about the y-axis, I have to see mirror images on either side of the y-axis. So if I take the graph of the sine wave to the right and I reflect it across the y-axis, its mirror image would look something like this. Because that's not the graph on the left side, we know that sine of x is not even. It's not symmetric about the y-axis. However, if I take this graph here in quadrant 1 and I think about reflecting it not only about the y-axis but also about the x-axis, then I could see it would land right on top of this one. Or if I rotate this around 180 degrees, it's going to land right on top of what we have on the left side. Using the graph alone, we can make the hypothesis that sine is an odd function. We can prove that a little more explicitly later on. Let's take a peek at cosine. Notice that the graph on the right side of cosine is the mirror image across the y-axis of the graph on the left side. Because this graph is symmetric about the y-axis, we would say that cosine is an even function. And finally, looking at the tangent function, we can use these two ordered pairs to make our judgment. Notice that both the x value and the y value change sign as we reflect one point around the origin to get to the other side. So because this graph is symmetric about the origin, then tangent is an odd function. Now, if you did your due diligence and you learned the graphs well in Chapter 2, that's going to assist you in remembering which functions are even and which functions are odd. According to our hypothesis, we determined that cosine of x was an even function. This means that cosine of negative x is equal to cosine of x. Now, where does that come from? We're simply observing that if cosine is even, then it's going to obey this algebraic test. And it does. Now, because secant and cosine have a reciprocal relationship, Secant is also an even function. So secant of negative x is equal to secant of x. Now, in addition to thinking about the graph of cosine of x, or secant of x for that matter, which are both symmetric about the y-axis, we can also make use of the unit circle to see this relationship. Let's look at the relationship between cosine of an angle and cosine of the negative angle. And I'm just going to pick on a 30-degree angle or pi over 6. Cosine of 30 degrees is positive square root of 3 over 2. So if I rotate in the positive direction to 30 degrees, I can obtain the cosine value by picking up the x-coordinate there. Now, let's change the sign of our argument. If I rotate in the negative direction, notice that cosine of negative 30 gives me the same cosine. So regardless of the sign of the argument, either positive or negative, the value of cosine will be the same. Therefore, cosine is even. From the graphs of sine and tangent, we made the hypothesis that sine and tangent were odd functions. If they are odd functions, and they are, then they will obey this algebraic test. That is, when I change the sign of the argument, I also change the sign of the function. Applying this specifically to our sine, cosecant, tangent, and cotangent functions, we obtain the odd identities. Sine of negative x is equal to negative sine of x, and similarly, cosecant of negative x is equal to negative cosecant of x. Tangent of negative x is equal to tangent of negative tangent of x, and cotangent of negative x is equal to negative cotangent of x. For the odd functions, which all have graphs that are symmetric about the origin, when we see a negative inside the argument position, it's equivalent to moving the negative outside the function. Let's observe this on the unit circle. This time I'm going to pick on a 60-degree angle. Let's look at sine of 60 degrees. So if I rotate in the positive direction, if sine is 60 degrees, I can see that the value of sine is square root of 3 over 2. If I rotate that direction if I rotate that amount in the negative direction, that is negative 60 degrees, so we're comparing positive 60 degrees to negative 60 degrees, and I observe the value of sine, notice it has a different sign than the original one. So when the angles are opposite in sign, the values are also opposite in sign. This creates a graph that is symmetric about the origin, and it also yields our odd identities. You will want to add these identities to your memory bank and devise a way to remember why they are true. Either use what you know about the graphs and the fact that even functions are symmetric about the y-axis and odd functions are symmetric about the origin, or use what you know about the unit circle and compare the function values when you change the sign of the argument. Now, let's practice this information in a couple of examples. In example 8, we want to determine whether the function is even, odd, or neither. So as you learned in algebra class, we're going to run the same test here. A function is even if, when we evaluate f of negative x and simplify, we obtain the original function f of x. A function will be odd if we evaluate f of negative x, and when we simplify, we get the opposite result of the original function. In either of those tests, notice we're starting out with f of negative x. So the first function we're going to consider is f of x equals sine of 2x over x. We need to evaluate f of negative x. So I'm going to replace all the x's in the original function with negative x's. So we're going to have sine of 2 times negative x divided by negative x. Let's clean up that argument a bit and rewrite it as sine of negative 2x divided by negative x. Now recall, sine is an odd function. Therefore, sine of negative 2x is equal to negative sine of 2x. Now we can cancel the negative in the top with the negative in the bottom, and we have sine of 2x over x. Notice that is identical to the function that we started with. Therefore, we can say this function is even. It passed the test for an even function. Let's try example B. We want to evaluate g of negative x and simplify. So I'm going to replace all of the x's in the original function with negative x's. So we have 2 sine of negative x times cosine of negative x. Now recall, sine is an odd function. So sine of negative x is equivalent to negative sine of x. Cosine is an even function. Therefore, cosine of negative x can be replaced with its equivalent cosine of x. If I filter that negative all the way to the left of the coefficient, I can simplify the expression as negative 2 sine of x times cosine of x. Notice this is exactly opposite in sign of the original function that we began with. Therefore, this function satisfies the test for an odd function, and we can conclude this is an odd function. Let's try one more example for good measure. Notice we always start with the same problem, that is replacing the argument with its negative version. So we're going to replace all the x's with negative x's. Remembering that tangent of x is a negative function, tangent of negative x is equivalent to 1 minus tangent of x. Now, when we compare this to the original function, we can see that this term changed its sign, but this term stayed the same. In order for this to be even, all of the terms have to stay the same. In order for this to be odd, all of the terms have to change sign. Because we got a combination of results here, we can say this function is neither even nor odd. So if we were to graph that function with our calculator, we would not see either symmetry about the y-axis or symmetry about the origin. Let's practice our identities some more on example 9. It says, use identities to simplify each expression. Remember, we have the reciprocal identities, the Pythagorean identities, and now the even and odd identities at our fingertips to use as tools to simplify these expressions. So on example A, we have sine to the fourth of x minus sine squared of x divided by secant of x. I notice in the numerator that we've got a greatest common factor of sine squared of x. Let's begin by factoring it out. When we factor it out of the first term, that's going to leave behind sine squared of x, and when we factor it out of the second term, that yields simply a minus 1. Now, the secant in the denominator we could recognize as 1 over cosine of x. Notice in our second factor, sine squared of x minus 1, we have the combination of the square of a trig function and 1. Remember, when that happens, think of your Pythagorean identities. Now, we know the fundamental Pythagorean identity is sine squared of x plus cosine squared of x equals 1. I want to manipulate the left side of that identity to match the factor that I have right here. So I need to subtract 1 from both sides of the equation, and I need to subtract cosine squared of x from both sides of the equation. Now I can see sine squared of x minus 1 is equivalent to negative cosine squared of x. This is going to simplify to sine squared of x times negative cosine squared of x. Now don't forget, here in the denominator, we still have the fraction 1 over cosine of x. Since we're dealing with a complex fraction, let's go ahead and simplify that by multiplying the top and the bottom by the reciprocal of that denominator. This is going to cancel the cosine in the bottom and combine with the power of cosine that we already have in the top. Now, on our next step, let's filter this -1 coefficient all the way to the left of our product, and we'll end up with negative sine squared of x. Combining these two powers of cosine, we have cosine cubed of x. And we have taken our original expression, which was in fraction form, and simplified it into a product. One question that you may have as you work through problems like this is, when am I done? How do I know that I have it in simplest form? Well, you cannot replace it with an identity that would create a simpler expression. There's no pending operations, and everything is reduced as far as possible. Your intuition will increase the more you practice. Let's try example B. We have cosine cubed of negative alpha over cosine cubed of alpha minus cosine of alpha. Let's work in the numerator first. In the numerator, I'm going to rewrite this just to be very clear. We have cosine of negative alpha raised to the third power. In the denominator, we could see that there's a common factor of cosine of alpha, so we could factor it out of both terms, leaving behind cosine squared of alpha minus 1 as the second factor in the denominator. Now, looking again at the numerator inside brackets, we know that cosine is an even function. Therefore, cosine of negative alpha is equal to positive cosine of alpha. Now, that function is cubed, so let's go ahead and rewrite it in the condensed form, cosine cubed of alpha. That potentially is going to simplify or cancel with the cosine of alpha we have here in the denominator. Now, working on this factor right here, notice we have the combination of the square of a trig function and 1. Let's think about our fundamental Pythagorean identity. Sine squared of alpha plus cosine squared of alpha equals 1. I want to make the left side of this equation match the factor that I have right here. To do that, I need to subtract 1 from both sides of the equation and subtract sine squared from both sides of the equation. So we can see now that we can replace cosine squared of alpha minus 1 with its equivalent negative sine squared of alpha. Let's go ahead and reduce a common cosine factor. I'll be able to cancel one cosine factor with the numerator, changing that exponent in the numerator to 2. This yields a cosine squared of alpha in the numerator and a negative sine squared of alpha in the denominator. That's pretty simple, but do notice I could replace this by a single trig function. Recall that cosine of alpha over sine of alpha is equivalent to cotangent of alpha, so we could replace that entire fraction with negative cotangent squared of alpha. So hang in there, guys. We've got a couple more examples to do. I want to provide plenty of examples so you'll have a lot of experience as you get started on your homework. In this example, we've got the squares of trig functions and a 1. So I'm automatically thinking about our Pythagorean identity. I'm going to jot it down once again in case I need to manipulate it. Sine squared of x plus cosine squared of x equals 1. Now, what I notice from this problem is that the denominator is completely in terms of cosine of x, and the numerator is a combination of sine and cosine. So I'm going to attempt to rewrite the entire numerator in terms of cosine to see if I can simplify. Noticing from our Pythagorean identity, we could isolate sine squared of x by subtracting cosine squared of x from both sides. So sine squared of x is equal to 1 minus cosine squared. So I'm going to take this expression and replace its equivalent sine squared in the given problem. Sine squared becomes 1 minus cosine squared of x. Now remember, we already had a minus cosine squared of x in the numerator, so I'm going to make sure and copy that down. And in the bottom, I'm just going to leave it as is, 1 minus 2 cosine squared of x. Now, maybe you see it in a flash. The two minus cosine squareds in the top are going to combine to give us 1 minus 2 cosine squared of x. So we have the same factor in the numerator and the denominator, so the entire expression reduces to 1. Isn't that interesting? This expression is a fancy way of writing 1. And we will finish with example D. We have 1 minus secant squared of gamma divided by tangent squared of gamma. For a problem like this, it's often convenient to rewrite everything in terms of sine and cosine. So I'm going to rewrite secant squared as 1 over cosine squared of gamma. I'm going to make my main fraction bar a little longer, and I'm going to rewrite tangent squared as sine squared of gamma divided by cosine squared of gamma. Now recall, when you have a complex fraction with 4 levels, and the fraction in the top and the fraction in the bottom have the same denominator, they will eventually cancel. Applying that shortcut here, we can see that this leaves us with 1 minus 1 over sine squared of gamma. We can replace 1 over sine squared of gamma with its reciprocal function, cosecant squared of gamma. Now, that's pretty simple, but again, we have the combination of the square of a trig function and the number 1. So let's go ahead and recognize the Pythagorean identity related to those two terms. We know that 1 plus cotangent squared of gamma is equal to cosecant squared of gamma. So I'm going to manipulate the left side of this equation to match what we have over here. This means I need to subtract cosecant squared of gamma from both sides of the equation, and we need to subtract cotangent squared of gamma from both sides of the equation. Thus, we can replace the 1 minus cosecant squared of gamma in our problem with its equivalent negative cotangent squared of gamma. As a single trig function, it's a little simpler than the two terms from the previous line. All right, you made it through our first section on identities. You're a trooper for making it through all of these examples. You are ready to get out there and work some homework problems.